A couple of weeks ago I posted a video about this motor. It's a 220 to 240 volt rated DC rated motor, 1.5 horsepower, potentially it pulls up to 5 amps. And the problem which I mentioned at the time was I didn't have a power supply that goes anywhere near 220 to 240 volts DC. So I did mention at the time that I might try rectifying with a site transformer, rectifying that into DC, albeit not smoothed at the moment. So that's the setup here. Let's just see this run. So here we go. By the way, I've got a clamp meter there. You possibly can see the needle deflect as I turn it on. It's going to draw a large current when this is turned on. There we go. And the motor's running. So this is currently being powered off from the site transformer through the bridge rectifier, powering this. Now, a site transformer converts the UK mains voltage, which is about 240 volts, drops that approximately in half, so we're looking at about 110 or 120 volts down this white flex here. Then we're going to go through the bridge rectifier and then supply the motor. Let me just stop this. Also, just in case you weren't wondering, yes, I have unplugged it before I touch anything. Okay, so let's have a quick look in a little bit more detail about my setup. So I've got the live of the, say, let's call it 110 volts. So the live of the 110 volts goes through this thermal overload. It's a 6 amp rated thermal overload, so it will continuously supply 6 amps, but it will, if you try to draw more than 6 amps on a longer basis, it will trip. So for example, if this motor were to stall, or if I were to do something silly with the configuration of this, hopefully that's going to trip out. Okay, so that's the first thing. Then I have just wrapped the live a couple of turns around the clamp meter just so I can make a non-invasive measurement of the current being drawn. Then we take the live to one of the two, it's got two AC inputs here, so one of those, so I take it to that one. Diagonally opposite, I take the neutral back to my site transformer. And then the diagonally opposite, other two diagonally opposite, I've got my positive supply and my negative supply, which then go to the motor. The protective earth, put a strap, tapped it, put a strap onto the motor just in case anything amiss happens. For example, if say the live were to touch the one of the DC outputs, you know, I think it's better to have a protective earth. What else? Well, I need to just mention why I'm using the site transformer. Bear in mind that this is a DC motor, so 240 volts DC means 240 volts DC. Now, when we talk about AC voltages, we're normally talking about RMS voltage. So, for example, let's just look over, hopefully you can see this. So if we said 240 volts, just see if I can get rid of the reflection. So if we said, say, 240 volts main supply, 240 volts AC, that's really 240 volts RMS, so 240 times, we would say root 2. The actual peak voltage would be 339 volts, which some people don't seem to realise. Now, 339 volts, if I bridge rectified it, would give us a maximum peak voltage of 339, which is well in excess of what we should be supplying to this. Now, I know that on average it may be much less than 339. In fact, it would be, on average, it would be 240 volts, but the peak is still in excess. So, and I'm not sure about this motor whether it would actually be okay with peak voltage in excess of this, because after all it's rated as a DC motor, not as a bridge rectified but not smoothed AC supply. So if I use, say, the 120 volt supply, and then I work out what the peak voltage is of that, so 120 volts times root 2 again, that will give us 169 volts. So 169 volts is well within the spec there. So if I bridge rectified it, my peak voltage will be 169 volts. The average DC voltage will be 120 volts. So that's okay. And even if I've got, say, 110 volts, because really site transformers are 110 volts, that's what we normally say anyway, times √2, and that's going to give me a peak voltage of 155, or an average DC voltage of 110. So yeah, okay, that is half of the supply voltage there, but still, yeah, I'm okay with that. And as you can see, that it actually runs okay. Now, if I can just do this one-handed without holding the paper down, let me try. So, if this were our original supply like that, once we've bridge rectified it, it's going to be like that. We will have discarded that part. The peak voltage is going to be the voltage RMS times √2, and then so the RMS voltage, the RMS is going to be the voltage down there. What else? Well, if I added some smoothing capacitors rather than having this very lumpy output, I could. The capacitors are still going to discharge. It's going to be more like that. So depending on what value capacitors, so I could have a little bit of smoothing as well if I have capacitors. Now, I haven't done that at the moment because just today I wanted just to see how it runs without having any capacitive smoothing. And generally speaking, I would say that I feel okay with that. So just one more time then, just in case you're interested, let's just plug in. There we go. Okay, and there you go. As soon as you've got the initial inrush current, basically you've got the stall current at the start when the motor's not turning, and then when it settles down, we're pulling about 1 amp. Now, got to be quite careful on this, but if I add to the load, I don't want to press any harder because fingers are getting a little bit hot there, but if I add to the load, you'll see the current goes up, and if you press significantly hard, you can probably get it up to about 4 or 5 amps without much problems. As I say, I think that's quite intrinsically dangerous, pressing against that flywheel, so really I want to keep my fingers away from it, so that's as far as I'm going to go there. And then the whole thing actually is intrinsically dangerous at the moment. Let me just remind you of that, just in case anyone's going to do that. All of this is currently live and should definitely be placed inside the case, so don't do this yourselves. Okay, that's it.